Hi, I'm Vladimir Kozlov, and here Igor Veresov. We are from Hotspot compiler group. This presentation is about ahead-of-time Java compilation, which was introduced as a new experimental feature in JDK 9. We will present AOT overview, Graal changes, phases of AOT compilation, and latest performance results. Safe statement. Main motivation for AOT is essentially provide fast startup for Java-based JIT compiler, which we are planning to replace in the future C2. Currently, we're using Graal for that. It also helps reach peak performance faster because you skip interpreter and executed compiled code. AOT code could be shared because a code section is read-only and in shared libraries. And code cache size could be reduced, especially when you have static compiled code which don't trigger a compilation, so you can use smaller heap for JIT code. New GUTC tool for AOT compilation was added to JDK installation. It used Graal as a Java compiler and code generator. It's only available on Linux x64 in JDK 9, where AOT is supported. And here's an example of instruction how to use it. Essentially specify module names, list of module names, classes, or jar files. And you also can add compile commands file where you filter out, specify, and exclude or compile only methods. Two types of AOT code could be generated depending on compile for tiered flag. By default, not tiered code, similar to what C1 generating client is generated. It's best to use, as it doesn't have profile collecting code, so it's best to use for short running application, and it's good for startup. And second type is tiered code, which similar to what tier 2 C1 generates its profile, invocation, and back branches. It should be used if you want to trigger high performance JIT recompilation to reach peak performance. Currently, there is limitation how AOT code should be used. The same VM runtime configuration, hardware configuration should be used during AOT compilation and execution. It is because when you do AOT compilation, you're running JVM and use runtime for particular system you're running on to generate to use instruction available on this machine, and also code specific to, for example, use GC. So when you execute AOT code, you have to use the same flags and the same setup, hardware setup. Otherwise, for example, you can generate code which use a VX instruction, but when you try to run it on another machine which doesn't have it, you crash. In the future, we want to introduce AOT cross-compilation where you specify targeted runtime configuration. And also, since when there is Java update, you have to recompile your AOT libraries for the same reason. There are two ways to load AOT library. It specify using AOT library flag, and another one, AOT aware of the well-known libraries installed in Java installation lib directory. It looks for particular names which contains following module names. Currently, users himself have to compile and create this library and install it. And another one, AOT first looking for well-known library in Java installation directory, and only then on library specifying on flag. So if you want to test new AOT library with the same classes and installed one, you have to remove installed one first. AOT also recognize some runtime configuration encoded in library names. There is for configuration which specify G1 or parallel GC used or compressed oops used or not. So only these four configurations. And essentially, in GDK 9, we support only parallel GC and G1. Actually, Chris Salinger tried CMS in Twitter, and it works too. So, more details. When AOT library loaded, code is not moved. Code section AOT loaded to library treated as additional code cache heaps. And when we traverse command method, we do it the same load, we traverse all these code heaps. AOT code follows the same invocation, deoptimization, and unloading rules as normal JIT compiler. And we may not remove AOT. I mean, there is link from method descriptor to the AOT code separate field. And we may keep it even when we switch to JIT code, because when we deoptimize JIT code, instead of going back to interpreter, we want to go to AOT code instead. But there are cases, for example, class redefinition, or some other cases where we cannot use anymore AOT code, so we mark it as not entrant. We have fingerprint recorded for each AOT class, and we compare it where class is loaded, and if it does not match, we don't use this class. So now we talk about Graal changes.
Hello. So in order to make Graal work as a general purpose AOT compiler, we had to make a few changes to handle constants, class initialization, add tier compilation support, and do some tweaks to the inlining policy. The biggest difference between the code that is generated by a JIT and the code that comes out of the AOT compiler is how they handle constants. JITs are usually able to just embed constants into the code. With AOT, we want the code to be mutable in order to be shareable. So for runtime constants that change from run to run, we cannot simply patch the code. We have to use indirections. At a high level, there are three kinds of constants that we have to deal with. There are performance-sensitive constants that actually can be embedded into the code and speculatively assumed to be never changing. Those are things such as field offsets, GC barrier choices, etc. We validate those constants when we load the library. We depend on class fingerprinting, heap layout parameters, command line flags, basically the state of the VM to verify those. Then there are global constants, things such as heap top end pointers, card table base pointers, etc. Those are eagerly initialized when we load the library. We abstracted them away with the new node that basically folds into a constant in JIT mode, as you would expect, and is lowered into an indirect load in AOT. And then there are local constants, things such as classes, objects, method counters that we need for tier compilation. To handle local constants, we use automatic constant replacement, which is a phase that is run late in the compilation pipeline after all the constants have been exposed. We replace classes and objects with resolve constant node that does lazy resolution. We replace method counters with resolve method and load counters node that resolves the method, allocates the counter structure if needed, and returns it. There are some well-known constants that are eagerly resolved and automatically replaced. For example, this happens for primitive array classes. We also have a phase to replace class mirror constants with indirections through class constants. A bunch of optimizations happen during constant replacement. Currently, there is at most one resolution of a constant per method. It is placed in a block dominating all the uses, and although it's optimal for code size, it may be too eager, and we plan to experiment with a better scheduling approach and node replication. We try to reuse dominating class initialization nodes. More about those in a minute. We also do simple optimizations. For example, we avoid full-blown constant resolution for the class of the root method holder and any of its superclasses, because it's guaranteed that by the time the method is run, those are resolved and initialized. In the end, constant resolution node lowers into the following construct, which is basically a load, check if it's null, and if it's null, call runtime. Our current AOT implementation doesn't do any kind of heap serialization yet, so we have to do all class initialization at runtime. We added a special plugin to Graal parser to be invoked at class initialization points, at which we insert initialized class nodes. We try to reduce the number of nodes that ends up being in the graph in various ways. During parsing, we avoid inserting nodes for method holder, class, and its superclasses. There is also a separate phase that we have that does data flow analysis and removes redundant class initializations. It's also good in combination with loop peeling, and it allows us to get initialization nodes out of the loops. In the end, its initialized class node is lowered into the same if null then call runtime diamond, similar to what happens with resolution. In order to fully integrate with the hotspot runtime, we had to support tier compilation. Basically, we profile method invocations and back branches similar to what happens at level 2 profiling. Profiling nodes are inserted in the parser using a special plugin. Later, these nodes are processed in a phase that assigns inline identification frequencies and random sources. More about those random sources in a minute. There are two styles of profiling that we support. There is the normal way of profiling, which is just what you would expect. It's load the counter increment, store the counter back, mask it if the result of masking is 0, call runtime to maybe invoke JIT compilation. We also introduced another way of doing profiling, which we call probabilistic profiling. And it's an experiment that has a goal of minimizing cache line ping-ponging. Consider a scenario which is very common in real life, when there are a bunch of threads running pretty much the same code, say serving web requests. If they're running the same methods, they would use the same counters. As a result, the cache line that contains the counter will have to move from one core to another when the store happens, and it is very problematic, especially in numerous systems. So the idea behind the probabilistic profiling approach is not to touch this cache line every time, but to do so only once in a while with some specified probability. To do that, we need branch and random, which is implemented as follows. Here, prob log is a power 2 log of the inverse of the probability. So having branch and random, the profiling code looks like this, essentially normal profiling wrapped in branch and random. There's seemingly a lot of arithmetic, but it actually all constant folds. So pay attention to this random function on top. It is what we would need to implement to make it all work. To cheaply implement random, we start with introducing a random seed node that lowers into RDDC on Intel. Although it's a reasonable random source for our purposes, it's too expensive to use in loops. So for loops, instead, we insert LCG pseudo-random generators, which essentially mull and add. Turns out that some arithmetic is way better than touching memory. It pays off a great deal, and this approach results in about 30% speed up on several benchmarks on NUMA systems. Lastly, we had to adjust inlining policy a little bit. Graal's default inlining policy relies pretty heavily on profiling information, block frequencies in particular. And we haven't made AOT compiler to consume such profiling information yet. So we had to reduce the inlining depth and do other tweaking. We also don't record CHA information for AOT methods. So we replace some CHA inlining decisions with runtime checks. Otherwise, inlining only happens for exec types, which actually was a surprise for me that it covers about 80% of the cases. So it's reasonable. So that's all for Graal changes, Vladimir.
Let's talk about AOT compilation phases, which happens in JUTC tools. So we have initialization, collecting method to compile, method compilation, converted, generated, compiled code to AOT code, and generate finally shared library. After classes are based on command line loaded, we look through all methods and filter them if you specify compile commands file. After list of methods is created, we fork up to 16 threads of Graal and start compiling it. This is most memory and time-consuming phase because we have to keep results of all compilation until the next phase, and for when you compile Java base module with all methods compiled, it's about more than 50,000 methods. So you have to specify up to 4 GB Java heap in this case. And it's maybe time consuming too if you have very large methods with a lot of bytecodes. For example, we have trouble to compile automatically generated system module jigsaw methods. We cannot use AOT code as it is. We have to modify. For that, we copy it in local buffer after it's compiled, and replacing, for example, calls with calls to trampolines. And these trampolines load destination from read-write sections, which is initialized during runtime lazily by runtime. We also replace constants, such as pointers to classes, methods, and strings, because also we cannot embed it, as Igor said before. And we initialize pointers with 0 during startup, during generation, and when we execute lazily and hit this code, when you see, for example, loaded class pointer from memory and 0, we jump to runtime, resolve class, and store resolved pointer to this memory location. So next time we just loaded it and continue execution without runtime call. We store names of classes, methods, and strings in UTF-8 format in AT library, and these names are used during class resolution, method resolution, and also string allocation. After we modified code and collect all data, we also call to runtime. Call to runtime to get fingerprints and metadata about methods. After all this data collected, we record runtime configuration, VM version, and we start we generate object files, and then we use local linker to generate shared library. Usually Linux has a linker by default in GC, but Mac OS and Windows, you have to make sure it is installed. Some system we are testing missing them, so we fail in AT testing. AT library is standard shared library, so you can use existing tools to look on them. You can use, for example, readelf to look on section. You can use dbx to look on, to print compiled AT method to look on them, and you can use object dump to disassemble code in AT library. Sections names listed, for example, here could be changed in the future. We changed them in JDK 10 already to shorten them. And we can add new sections, so not rely on this output too much. We have test scripts in hotspot test directory which build AT library and test them, so you can use it as example, and there is README there explaining how to run tests. Now let's talk about performance. This slide describes settings which are used to run to collect this data. The main point is that we use touch methods for AT compilation. We did several experiments, compilable methods, for example. We create, for Java-based, it creates something like 300 megabytes AT library in this case. And it affects startup and execution because you have a lot of methods there. And when you load in class, you have to search corresponding method, Java method, and it takes time. So the best result for startup and execution, we found that it's better just use touch method. It means a method which you executed during testing run. This slide shows execution time, real time running Java Hello World. So time is milliseconds and smaller value is better. Main observations that AT improve, on average, improve startup about 5% and class data sharing about 20%. And combining, we have up to 25% improvement. First column shows the data collected for C1, which is enforced by tiered stop at level 1 flag. Second column is default C1 plus C2 tiered configuration. And third and fourth column, letting other sets, is C1 plus Graal as JIT. Yes? Up CDS. It's much better results. Yes. It's actually said that it's combined Java-based plus Graal CDS generated, which you can do with up CDS, but not with CDS. So third column and fourth column, it's Graal plus. Can I scroll? Okay. Second set about AT set, it's For C1 case, static AOT is used, so no profiling. For C1 plus C2 was tiered AOT, and for C1 plus Graal, both cases is used. The third and fourth column in this set shows that tiered AOT has penalty about 10% because you have to profile. This is why it's different. The third set for CDS, if you look on for Graal result, it shows that when you use Java-based plus Graal CDS combination, performance is worse. It's the same as AOT. Essentially, CDS archive size and number of classes is almost triple. So you have to spend a lot of more time to processing this data. This is the same runs, but user time. It's combined CPU time. It shows that AOT use much less CPU power because it does not trigger JIT compilation during this time. So essentially, if you look on CPU percent, it's running just one thread, Java thread execute application using AOT code. And if you look at normal case, you see that second and third thread also active doing JIT compilation. Next data, it's slightly longer running application, about 2 seconds. It's Java-C compiler and JVM CI files. But result is very similar to previous data. Third column in the second AOT set shows that AOT code for Graal helps a lot. This is our main motivation. So if we compile Graal with AOT and use it, it's on the pair with C1 and C2 combination. This is, again, user time, which again shows that AOT code helps with CPU resource consumption. And next, it's Ruby runs. It's also about small hello world script, which is also around 2 seconds. This one shows that CDS helps a lot, up CDS helps a lot. It's up to 30% better for default case C1 plus C2, and for C1 case, it's up to 40% improvement. In all these CDS cases, Java-based plus contains Java-based and JRuby classes together. And again, the same story with user time. Now about peak performance. How AOT and CDS affect peak performance. I use spec JVM 2008. Its runtime is quite simple, reasonable, and setup very simple. I reduce it warm out time, iteration time, and number of iterations. Experiments show it's enough time to JIT compile during warm up, so and reach peak performance. I use combining score at the end to compare results. And the other stuff is similar for startup benchmarks running. On these slides, higher value is better. Main point here is that AOT, which is pointed by arrow, tiered AOT in default case C1 plus C2 helps to reach the same peak performance as default case. So in previous slides, you saw that AOT helps faster startup. And as you show, it does not regress peak performance, or even you get slightly maybe better peak performance as in default case. Also, tiered AOT plus Graal performance is about 10% worse than C1 plus C2, which is expected. It gives better results in some benchmarks, such as XML transform, but there are some worse results, which small sub benchmarks. Next. General observations about performance data. Short-run application give better results with C1 plus CDS and static AOT. We got best AOT results when you compile AOT only touched methods, because AOT library, it's reasonably small and all executed methods usually cover it. With tiered AOT, we reach the same peak performance as currently we have. Static AOT code, especially static AOT code, consume much less CPU resources. Code generated by Graal, it's about 10% slower, currently 10% slower than code generated by C2. This is work in progress. We planning only on the replacement of C2 when we get the same or better performance. It seems to have compiled Graal even by just static AOT is enough to get results we want. CDS, CDS improve a lot, much better than AOT startup performance. And benefits of AOT and CDS incremental, so improvements add up. We had some restriction for JDK 9, how and when you can use AOT, and we're working on to address them. Currently, we added support for macOS and Windows on x64 in JDK 10. We removed dependency on libelf tool and used Java code to generate object files. It was done because we need to support also macOS and Windows. We are investigating using data from CDS archive in AOT code. For example, we experimented to use class pointers initialized during AOT because it's not moving when during execution CDS archive is loaded, so it's the same pointers. But we found out that we still have to do class resolution anyway to construct or populate system dictionary and other VM tables, so we don't see much benefits from that. We also experiment to populate string pointers, essentially to do serialization, object serialization. CDS allow to do this with G1. And we try this, and it seems it helps, but not in default case, where only several hundred strings store it in CDS archive. But if you store all strings in classes, then it may help. So some results show that it may help a little, but still can help. And we work also on invoke dynamic support. We have some problem to compile method with invoke dynamic. And that's all questions. Okay. The question, how many methods I have to compile for hello world? With AOT, yes. So from my head, I would say something like 2,000.
Do you just compile every one of them, or is there any heuristic that
No,
found?
for all this experiment, we do training run, and they raise flags in VM, print touch methods, something like that, which at the end create output with list all methods which executed during run.
Every method.
Yes, which are executed.
I see. Yeah, it's a natural.
Yes, but you do have to do training runs for that. It's actually the same for app CDS. You have to do training run to collect used classes. Otherwise, it's only about 100 system classes, which is not enough.
So I have done exactly the same thing as you, which is if you try to compile everything, it's really too big. You have to, compile, doing a training run and then compiling what you are running.
Yes.
Should be the default things.
Yeah, but
it should.
You have to get somewhere a list of methods.
Yeah, and now what I want.
And you have to specify this list using some options, flags for JTC. By default, AOT tool, you can just give class and it compile all methods there. This is default. When you have to specify flags, I don't think it's defaultness.
If you compile everything, it's not going to be like super bad, but
it is because it's really big. And,
it is.
And the startup, you have a price at startup just to load everything.
Yes.
Yes, a good SSD is recommended, but.
And the other thing is because you are doing training run, you have more information, you have the profiling information.
Yes, Igor mentioned
We don't do that though.
You should.
Yeah, we should, but currently we don't.
For experimental purposes for JDK 9, the simple instruction is better, I think, for people to try. And essentially, it's later on, people understand what's best to do. And we do it in documentation to describe.
I have a question on class fingerprinting. You use fingerprint to prevent execution of code of classes that change. Suppose this code is unlined. What are you going to do?
If it's unlined, the outer method will be made not tangent. We record dependencies on inlinees and static fields that you use as well.
Question for Igor. Randomized profiling, you said that 30% performance improvement. Was that the randomization compared to the hardware randomization, or was it the 30% improvement as a result of randomized profiling?
Over normal profiling.
Normal profiling being
normal mean you increment every time. So if you don't increment every time, that's the difference basically. Yeah, so I think the results were for maybe startup benchmarks in JVM 2008 or something, and
yeah, it was 2008.
That's where the number 30% comes from. The difference between the code with normal profiling versus probabilistic profiling is probably even bigger, but I don't have exact numbers. If you
what is default mode?
Probabilistic, you can turn them off on. Graal probabilistic profiling equals true false. If you're running in a single threaded mode, perhaps normal profiling is can be a little better sometimes. But if you're running something multi-threaded, then probabilistic profiling is way, way better. So it's sort of a hybrid between sampling profiling and exact profiling.
Okay. I got here a little late, so I apologize if I asked something that didn't get covered in the talk. But I was curious as to how the AOT dealt with initialization semantics, particularly the lazy initialization that Java has. What was done there?
We, as I mentioned, we insert special nodes that do initialization at initialization points. So when that happens, I don't know, allocation, static field access, static methods, static method calls, yeah, we have a special check whether the class was initialized. So it's a runtime check.
So essentially we talk that we replace it immediate class constant in code. You usually see in JIT code with load from memory and null check. If it's null, which means it's not initialized yet, we jump and call runtime, which does resolution and populates this memory, so later on it's load class
So
pointer.
in the future, if we maybe do heap serialization, you can run static initializers at static compilation time, and then you can emit initialization checks.
Quick question for Igor. The probabilistic profiling, what was the problog value you used? Is it dependent upon the number of CPUs? And if so, how does it vary?
Which probability?
No,
when
we
you do
don't
probabilistic
check.
profiling, how do you initialize the problog value?
It's a compile time constant.
Yes, but what is it? What
I
value?
ran a few things and decided on the value.
So what's the value you're using?
I remember maybe 8. So each. Or
Okay,
maybe
and you were
six,
running.
I think 7.
Okay.
7 or 6. So every 128th time or.
Okay, and you were running on an 8 CPU machine, 4 CPU machine.
It was probably something bigger.
Okay, thanks.
It was a 2-socket Intel, maybe, I don't know, 8 cores each or.
Thanks.
Thanks. It's early and I'm under-caffeinated, so apologies if this is a stupid question. With respect to the probabilistic sampling, it seems to me that, why did, one could imagine bumping thread local counters and periodically flushing them back, and in so doing you wouldn't have like the sloppy counter, you would have exact values so long as you flush the thread local one back to the global one, and you would have less in terms of cache ping-ponging. I'm curious about the intuition behind, like, not going with that, but instead doing the probabilistic sampling approach.
Well, it doesn't have to be exact. In fact, even with normal profiling, it's not exact because the increments are not synchronized. So if you do it in parallel in many threads, you will increment the same value essentially and store. So there will be a lot of missing counts even in normal case. Then if you can certainly, like you said, accumulate increments and then maybe at the end of the method or in some like post-dominating block, flush them. We actually plan to do that to optimize profiling even further, but I don't know, it just seemed like a fun thing to try and it paid off.
That's totally fair. Yeah, thanks.
Last question.
Well, 30 seconds.
So I'd like to ask about fingerprints. Do you only do class level fingerprinting? Like if you have to invalidate are you able to invalidate only on a method basis, or do you have to invalidate the whole compile code for a whole class?
All code for whole class. So essentially, fingerprint calculated involving full class definition, constant pool, and bytecode.
I see.
So even if you change slightly bytecode, it will trigger remove AOT code.
So there's only a single level of fingerprinting?
Yes.
And so what if I just redefine one method in a whole class with lots of... Okay.
You throw everything away.
Thanks.
It's the same with JIT compilation. Essentially, if you do some redefinition, all in method will be thrown out.
Yeah, I think it's a lot worse with JIT compilation.
Yeah, with JIT compilation, it's worse. Okay. Thank you.